Right, so we're graphing complex numbers. This is something that pops up a lot in the exams in complex numbers. That and De Moivre's theorem are really the things that you see a lot of repeated. But being able to sketch complex numbers is really, really important. So the thing to look at here for relations and regions of the complex plane is the way that these expressions are written. They're usually written as a kind of restriction on z, like a set, and you're told that z is such that any information about z. So here it says real z equals 6. Real z equals 6 would actually look like this. So for every real, we'll go up to 6. That's our real axis. So real values being 6, that would actually be not just the point here on the axis, but any point all along, either way, this way. It doesn't matter what the imaginary part is. The real part is 6. So this particular graph, real z equals 6, is actually this straight line, and it's equivalent, if you think of it this way, to x equals 6. That's what it's equivalent to. So for all values, the x part is equal to 6. So here we're going to be looking at a set of points which satisfies the given conditions. It's called a locus, and it's a graph, but it's called formally a locus. A solid line is used for a boundary which is included in the locus. This is very important because it's that idea of sketching regions. So if you've got a greater than or a less than, you're going to use a solid line. If you have a less than or a greater than without the equals, you're going to use a dotted line, and that's for a boundary which is not included. Okay, so it's just that difference between using solid lines and dotted lines for your regions. So we'll have a look at this example here, example 24, and sketching this one. There's two ways to do this. I'll actually show you both methods. The first one is using a sort of more algebraic method. So you've got S, sketch the subset S of the complex plane. That means sketch the points S which lie on the complex plane. It's not the entire plane, that's why it's a subset. And it's Z such that the modulus of z minus 1 equals 2. And we've got these braces around the expression. Now we're going to look at the modulus again. Remember that the modulus for z, just z, not z minus 1, is the square root of the real part of z plus the imaginary part of z squared. That's what the modulus is. So what we can do here is we can actually use this expression to help us solve this problem. So what we're going to do is let z equal, you can let it equal a plus bi, but we're actually going to use x plus iy. It's just going to help us because in terms of coordinates, you always think of this as x and this as y. So that's why it's good to use x and iy when you're doing graphs. So we're going to substitute that into this expression here. So let's look at what z minus 1 as a modulus is. Let's substitute z in, x plus iy, and the minus 1, because we've got that minus 1 there. Now, if we rearrange this, let's put the real parts together and the imaginary part together. There's only one imaginary part. So this is our real part, and this is formally that y is the imaginary part. So let's look at now using this expression. So the modulus of z minus 1 is equal to the square root of the real part squared, okay, which is x minus 1 squared, plus the imaginary part, which is y squared, like that. Okay, that's what we get. And we also know that all of this mod z minus 1, is equal to 2. So let's actually use this part here to finish this off now. So we know that this is the modulus here, that's what the expression is. And formally too, if you want to start getting into different notation, you can use a triple equals sign here. The triple equals sign doesn't actually give you information. It tells you that this is this. They're the same thing. Okay, so it's like saying a banana is a banana. You're not getting any new information out of there, it is what it is. So here, you can use a triple equals sign to say this is this thing, and that is equal to 2. So that's the just different notation if you want to get into that more advanced notation. So we can square both sides here. And what you'll see when we do that is we get x minus 1 squared plus y squared equals 2 squared, which is 4. And you'll recognise that, hopefully, because we did heaps of work on this. It's why we did heaps of work. It comes back again as a circle. Woo! And it's a circle with a centre. Where is the centre? 1, 0, translated that way 1. And the radius, remember the radius of a circle is always r squared here. So the radius equals 2. So we can actually sketch this now. We can sketch it as, or just put it here. Okay, do that again. Now you'll rule these lines so they're a bit better looking than mine. 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. So you can put these tick marks in so that you can actually keep track of things a bit better. So we're going to move our circle across 1, so that's going to be our centre of the circle, and we have a radius of 2. So 1, 2, 1, 2, 1, 2, and 1, 2. So this will be there and there. So when we sketch this, and I'll sketch this in a different colour so it's a bit clearer, you want to try and avoid having any pointy corners, it's a bit dodgy, and labelling, I'm going to label the centre here, which is 1, 0. Okay, you could also label the each of those points here as well, but it's enough here to just label the centre. Okay, so that's how you're dealing with a set like this. Using this is the substitution you'll use for all your graphing. Okay, so that's a graph substitution. Rather than A and B, okay, it makes more sense to use X and Y because that's what we're used to seeing Cartesian forms in, X and Y. So once you do that, substitute into your expression, use that relationship for the modulus. That's a really, really useful relationship for modulus that you will see. And then using a bit of algebra to find what the actual graph is, which is a circle. Now that's the first method. There is a second method which is a bit faster. So method 2. Method 2 actually looks at this graph, which is, and I'll do this in light blue, mod z minus 1 equals 2. What this says to you is that you have a point, z, which is translated across 1. So if you graph this, and I'll graph it here, you take your point z and you translate it across that way 1. This tells you the distance from the origin. So what this is actually saying in words is the distance from the origin from that, the distance from that point is 2 in every direction. Okay, this tells you the distance. So if you think about the only way you can have a distance from this point in every direction as being 2 is a circle where you're 2 out the whole way around the circle. So when you see this, think about distance from the point is 2, and if we know the distance is 2, the distance is 2 that way, 2 that way, 2 that way, and actually 2 in any direction, the only way that can be done is with a circle. So you can get there by using the idea that this is actually a distance from a point. And it's a more geometric way of looking at it. And at the end of the day, if you're just asked to sketch something, you don't need to show all the algebra. So if it's quicker for you to identify this is a circle, because it's a distance, it's translated across 1, so that's where the centre would be, and the distance is 2 all around that point, then it's just as quick to straight away draw your circle that way.